Welcome to today's Explainer. Class, I'm Dr. Chem, and today we are going to dive headfirst into the truly fascinating world of high-speed countercurrent chromatography, or HSCCC for short. If you're studying analytical chemistry, biotechnology, or pharmaceutical sciences, trust me, this is a technique you absolutely need in your toolkit. We're going to break down exactly how this incredibly powerful, support-free liquid-liquid partition technique works, and why it is literally revolutionizing the way we isolate and purify complex biological molecules. So, get your notes ready, and let's get started.
Here is our syllabus for today's session. We'll kick things off with a welcome to liquid-liquid chromatography, then cover the core principle of partitioning. Take a look inside the HSCC instrument, weigh the pros and cons, explore some real-world HSCC applications, and finally wrap up with a review and your next steps.
All right, Section 1. Welcome to liquid-liquid chromatography, breaking the solid support barrier. Let's address the massive, fundamental difference between HSCCC and traditional methods like HPLC.
So what is it exactly? HSCCC is essentially an advanced, supercharged form of conventional countercurrent chromatography. But the real magic, the absolute game changer here, is the phrase support-free liquid stationary phase. Think about traditional HPLC for a second. We typically use a solid stationary phase, like silica packed tightly into a column, right? Well, in HSCCC, both the mobile and the stationary phases are liquids. By tossing out that solid matrix entirely, we brilliantly avoid the dreaded problem of irreversible sample adsorption. Your sample isn't going to get permanently glued to a solid column support. This guarantees incredibly high sample recovery and purity, and there's basically zero risk of a solid support denaturing your super delicate target molecules.
Moving right along to Section 2, the core principle, partitioning, how centrifugal force drives separation. Since we just established there's no solid column, let's break down the underlying physics that actually makes this work so well. Now, you might be wondering, it's a great question, right? If both of our phases are liquids and there's no solid tube holding one of them in place, how on earth do we actually separate the molecules without everything just washing straight out of the machine in one big mess? Well, the answer lies in the dynamic interplay between two immiscible liquids, think oil and water, combined with some seriously clever engineering. It really comes down to the partition coefficient, or what we call the K value. Simply put, a target molecule will naturally divide itself between the liquid stationary phase and the liquid mobile phase based on its unique K value. Because we are using two immiscible liquids, they naturally form distinct layers. So when we inject a complex mixture into the system, each unique compound within that mixture is going to show a different preference or affinity for either the mobile or stationary liquid. This exact difference in solubility is what allows us to cleanly isolate our target compounds. But wait, we still have to hold that stationary liquid in place, right? To pull this off, the machine uses high-speed planetary rotation, literally like the Earth orbiting the Sun while spinning on its own axis. We take a long Teflon tube, wind it into a tight coil, fill it with our liquids, and spin it really fast. This complex double-axis rotation generates an Archimedean screw force. As the coil spins, it creates these continuous, alternating zones of vigorous mixing and settling. The strong centrifugal force effectively locks the stationary liquid phase securely in place inside the coil, while simultaneously allowing the mobile liquid phase to be pumped continuously right through it. It's basically a continuous, dynamic liquid-liquid extraction happening thousands of times along the entire length of the tube. Okay, Section 3. Inside the HSCC instrument, the mechanical breakdown. Now that we've wrapped our heads around the physics of planetary motion and partitioning, let's peek under the hood at the actual machinery. Just like a standard HPLC setup, the workflow here is highly systematic. Notice how the sample follows a very tightly controlled linear path. First up, we prep our biphasic solvent system in the solvent reservoirs. Next, high-pressure pumps force the mobile phase through an injector, which is exactly where our sample is introduced. That sample is then swept into the rapidly rotating multi-layer Teflon coil, where all that dynamic mixing and settling magic happens. Finally, the separated compounds elute right out of the coil, passing through back pressure controls and into a UV-visible or mass spec detector, where our computerized data system logs the results before the fractions are safely collected. To put a visual to all this, take a look at a commercial unit, like the HSCC 3000 series. From the outside, it might just look like a standard, unassuming lab cabinet, but inside that compact, temperature-controlled box is a highly engineered centrifuge housing those spinning centrifugal rotors and Teflon coils.
This specific kind of setup generates the intense revolution speeds necessary to keep that stationary phase perfectly stable, which in turn lets us push the mobile phase through at much faster flow rates than older, conventional countercurrent methods.
Section 4. Weighing pros and cons, a critical evaluation. As scientists, we always have to critically evaluate our tools, right? So let's honestly weigh the trade-offs of using this in your lab.
It's definitely a delicate balance. On the advantages side, HSCC gives us unparalleled separation efficiency, rapid analysis, and phenomenal sample recovery. Because there's no solid support, there's no irreversible adsorption, meaning you get nearly 100% of your injected sample back. Plus, scaling up from tiny analytical milligram batches to massive industrial kilogram preparative scales is super easy. You basically just increase the tubing volume. However, you have to balance all that against the limitations. The sheer complexity of optimizing your two-phase solvent system can be a major headache. Finding the exact right mix of solvents so that your target molecule partitions perfectly often requires a ton of trial and error, which leads to notoriously long method development times. On top of that, the high-speed machinery is definitely an expensive initial investment, and it can sometimes struggle with efficiency when dealing with highly complex mixtures.
Let's look at Section 5. Real-world HSCC applications, from plants to pharmaceuticals. Keeping those pros and cons in mind, where is this technology actually being put to work today?
Well, because liquid-liquid partitioning completely ditches harsh, solid matrices, it is uniquely, incredibly gentle. This makes it the absolute ideal method for isolating delicate, heat-sensitive, and biologically active molecules. In phytochemistry, it's widely used to purify highly bioactive phytochemicals, things like flavonoids, alkaloids, terpenoids, and polyphenols straight from crude plant extracts. Over in the pharmaceutical industry, it's a major go-to method for purifying natural antibiotics, microbial metabolites, drug intermediates, and delicate peptides. Basically, anytime maintaining the biological activity of an active pharmaceutical ingredient is absolutely critical, HSCCC is on the short list of tools to use.
And real chromatogram data proves just how effective this technique is. Here we can see the highly effective separation of two proteins, myoglobin and lysozyme. What's truly incredible here is that this separation was achieved using an aqueous two-phase system, specifically a mix of polyethylene glycol and potassium phosphate. These kinds of systems provide incredibly mild physiological conditions that completely prevent proteins from denaturing during the separation process. Just look at those clean, highly resolved peaks. You get high purity, high resolution, and totally intact biological molecules at the very end of the run.
And that brings us to Section 6, Final Review and Next Steps, your assignment. We have covered a ton of ground today, class, from the brilliant lack of a solid stationary phase to the mind-bending physics of planetary motion and Archimedean screws.
So, as we wrap up today's explainer, I want to leave you with a final provocative thought, and of course, an assignment. For your homework, I challenge you to critically compare the separation efficiency, cost, and sample recovery of HSCCC against conventional CCC and standard HPLC. Think critically about exactly how HSCCC solves the limitations of HPLC, especially regarding sample recovery and denaturation, but also consider how it advances beyond conventional CCC. Evaluate all these variables carefully, including the upfront costs and the headache of solvent optimization. When all the dust settles, which technique truly reigns supreme for the future of modern analytical and pharmaceutical chemistry? Take some time to review the differences, and I will see you in the next session to discuss what you find. Class dismissed.